Welcome back to the classroom. So continuing on what we were talking about in Module 3, Inquiry 3 about sound waves, we were analysing the relationship of sound as in nature, and we discussed about beat frequency. We'll continue on with the second part here, which is the Doppler effect. Now, as you can see with some of the diagrams we're using here, the Doppler effect is the relativistic effect or relative effect between moving objects and the sound. Okay, you can see from these diagrams here what we're showing is if an object is moving closer or towards you and they're generating a sound, we tend to hear a higher pitch and a shorter wavelength. If that object generating that sound is moving away from you, we tend to hear a lower frequency and observe a longer wavelength. You can actually apply the Doppler effect with light waves as well. So we know that blue light has a shorter wavelength, high frequency. So if an object is moving towards you and it's a light source, you'll see it glow more in the blue spectra of the visible light. If something's moving away from you, it'll become more reddish looking. And that's actually how we work out that the universe or the stars are moving away from us, and that whole expansion called red shifting. Okay, so let's just quickly explain how this occurs. So the Doppler effect is an increase or a decrease in the frequency of sound, light, any other form of wave as the source of the wave moves closer or further away from the observer. Now the reason why that's the case, I'll just scribble over this original thing. Say we have a sound source, okay, that's in the center. It's going to generate a sound in equal distance all around itself, equally distanced the sound. Okay, it's going to be projected in all directions. Now, if we move this sound towards us in this direction, you can see that in the direction in which this sound wave, this wavefront is being generated, you're getting closer towards it. So what actually happens is as it's still generating the sound, the object is moving closer to the wave of the sound wave it's generating. So it gets closer and closer together, and that's the reason why we observe this high pitch as the sound source or the light source gets closer to us. While as the wave it's generating behind it, because it's moving away from it at the same time it generates that volume, those waves are further and further separated from each other. So you get sort of this, instead of circular shape, we get this sort of oval shape that's favoring the side in which the speaker is moving towards. Okay, so this is what we kind of see. If it's static sound, you can see it's generating in all directions. You will find that the frequency, no matter where you're standing, is the same. However, if the object is moving, you'll find that the area in which the object is moving away from you to have a lower pitch or lower frequency, and the one that's coming towards you has a higher pitch, higher frequency there. Okay, so we can actually see this application in the universe. When Edwin Hubble first investigated things related to redshifts, we can actually see if the universe was in fact stationary, we'll find that the visible spectra, these lines will be relatively positioned exactly where we predict them to be based on their chemical compositions. If the universe was moving away from us, we'll find that the absorption spectra or emission spectra, all of that is more favoring the right hand side, the red spectra, hence why we call this the redshift. So it's just a couple of terms you would like to know out of interest. We don't need to know about redshifts just yet. So redshifted or redshift is when the spectra is favoring towards the left, and we have blue shift if it's favoring more the blue light, and this would imply that the universe is coming closer towards us. Okay, now just saying, the reason why we know that is we already know what chemical composition the galaxy should have. So if we know the chemical composition, we can work out what particular lines are we trying to see based on the results we have in the laboratory, and then we can compare whether it's been moved from the expected position. So if it's been shifted towards the red from where we expect, that would imply it's moving away from us. If it's shifted to the blue, it means it's coming towards us. Okay? Alright. So the Doppler effect refers to an increase or decrease in the frequency or the sound of other waves, and we give it in this notation here. So we have f prime, f prime is the frequency that you observe, so that's the observed frequency there. F is the original frequency you hear or see. F or v wave is the velocity of the wave. V observer, so that's whoever in the question you're looking at or yourself. How fast are you traveling? V wave there, and then minus V source. Now this negative here would imply that they are moving away from each other. So V negative source means we're moving away. What we were saying is the observer is going in this direction, and the sound or the source generating that sound is moving in the other direction to that person. Okay, so that's what we are implying there. Alright, the next one we have is just looking at the Doppler effect and particular relationships. So you can actually work out from the formula itself, if the observer is stationary and the source is moving towards you, what type of frequency would you hear? So say if you're the observer and you're not moving, and the motion of the sound is coming towards you, you'll hear that the pitch of the sound is higher, greater frequency. If it's moving away from you, it gets lower. So consistent to what we said before. If we're moving towards the source and the source is stationary, then obviously we will hear high pitch, because obviously that means we're getting closer towards the actual sound, and obviously if we're running away from the sound, then we hear a lower pitch. So everything's consistent to each other. Okay. Now here's the interesting thing, the arrows aren't shifting, but it doesn't matter. So if we have a jet airplane and makes supersonic sound, the reason for that, okay, the reason why it makes supersonic is because we get a speed that's faster than the speed of sound. So when anything travels faster than the speed of sound, it creates a thing called a supersonic effect or sonic boom. So that's what we have here. Because of the Doppler effect, sounds coming from a moving observer would see a higher frequency in the source if it's moving towards the observer, so don't forget that. So let's do some calculations to work out the frequency of this moving object here. Okay, so let's just find the individual calculation numbers. So we have an approaching ambulance has a frequency of that. So that's our F observed frequency. Okay, that's the one that's been generated. We know that the ambulance is traveling at 25 meters per second. A car is approaching the ambulance at 15 meters per second. What's the frequency of the sound heard by the occupant? So this 15 is the velocity of the observer, and they are approaching. Okay, so they are approaching each other, so they're coming towards each other. Okay, let's set out the equation. Okay, so setting out the equation, we have f prime f divided fraction divided by the speed of the speed of sound. Okay, so speed of sound source, so speed of the wave 340 minus plus the speed of the source, speed of the observer, sorry, so that's 15. 340 minus the speed of the source, which is 25. Notice they are, although it says approaching each other, they are actually moving away from each other, because as they're approaching, you can think of the car is going that direction, Anderson's going in the opposite direction, and we have a frequency of 800. Okay, put that in your calculator and you will find that the frequency that you hear is roughly 902 Hertz. If we have a racing car moving towards a stationary observer, so we have a stationary observer, the observer is 0 meters per second, car is moving at that speed, the engine is emitting a sound with a frequency of 1.8 kilohertz. What's the frequency heard in this scenario? So if that's the case, we have f prime is what we're trying to hear. 1.8 kilohertz is 1.8 10 to the power 3. Okay, divide by the speed, or we have the speed of sound, plus the observer, which is at 0, moving at 0. We have that, and we are moving towards a stationary observer. Okay, coming towards. Okay, and so we have minus 60 meters per second. Okay, so if we substitute that into our calculator, we get 2190 Hertz, which again is consistent to what we're saying, because if this object is coming towards us, we should see a far higher or far louder frequency than we did before. Okay, so that's what we get here. Alright, so our last question that we're going to look at, and by all means see how well you go with it. So the question we have here is, we have a super genius called Gus has devised an experiment to find the speed of sound in water. He has taken a motorized toy submarine and he is trying to work out, using the laws of the using the Doppler effect, to work out what the speed of the sound is in water. So you have all these particular values. Try and see what you get for the speed of sound. Okay? I'll give you 3 seconds to pause before I go through this question. Okay, so we might be a bit slow in space, but we'll see what we can do. Okay, so as it moves, we have a frequency of 1.7, but O'Grady or Gus here measures it at this particular tone. So f prime is 1.6, 10 to the power 3. The tone or the frequency that was originally generated is this one here. So that would imply that we are moving towards the tone, or as moving towards the sound source. As you can see, this is going down. V wave is what we're trying to find. Velocity. We know that the observer, if we have a look, is Gus moving in this question here. So submarine, he sets the submarine moving away from him. So our observer is not moving. Okay, so it's 0 there. And then the submarine is moving away from him at a constant velocity of 14. So this source is moving away from our observer rather than towards our observer. So if it's moving away from our observer, we can do it as minus 14, just getting the values right. Okay, so there's that. If we rearrange the equation thereon, we'll find that it's rearranged like so. So velocity of the water plus 14, 1.7 10 to the power 3, v water. Okay, and then you rearrange the equation from there. What you should find at the end is the velocity you're searching for is 1176 meters per second. Okay, so that's what we have. And that basically summarizes everything we've been talking about with the Doppler effect and the beat frequency here. So remember, beat frequency is the difference in frequency or the difference in amplitude when two slightly different frequencies superimpose to each other. The Doppler effect is the difference in frequency we hear because of a relative motion between the sound source and the observer listening to it. Okay, so hopefully that helps explain everything you need to know about beat frequency and Doppler effect in terms of sound waves. You're always more than welcome to replay this video and re-listen to any concepts that you missed out on. Anyhow, like always, thank you for joining in the classroom, and I'll see you next time.